In this video, we're going to discuss the relative strengths of acids and bases, return to this distinction between strong and weak acids and bases, and see how this distinction relates to pKa or pKb. To begin, let's talk about what we really mean when we say a strong acid or base versus a weak acid or base. We can quantitatively think about those two terms using pKa and pKb. A strong acid or base reacts completely with water to form hydronium or hydroxide and the conjugate base or acid of the species, respectively. So, for example, the strong acids, 6 of which are listed here, the 6 most important, react completely when dissolved in water to form H3O+. And so, for example, if we're thinking about the stoichiometry of a strong acid, we can think of it effectively as the entire number of moles of that acid becomes hydronium ion, H3O+. And if you think about what that means in terms of the acid dissociation constant, well, the denominator of that is the intact acid, for example, HClO4, perchloric acid. And in the numerator, we have H3O+ and ClO4-. Complete dissociation means there's no HClO4 left. And so K is effectively infinite in that case, infinitely large. And that means pK is negative infinity, more or less. Now, in practice, strong acids have pKa's that are quite negative, -10, -7, -5. And really, 0 is a good benchmark. Any pKa less than 0 corresponds to a strong acid. And likewise with bases, it's just now strong bases react or dissociate to produce a full equivalent of hydroxide with respect to the base. So these group 1 and group 2 metal hydroxides, for example, that you see here, dissociate completely to form hydroxide, either one equivalent in the case of the group 1 compounds or 2 equivalents in the case of the group 2 compounds with calcium, strontium, and barium. And here again, we think about the pKb of these as negative infinity, right? They react entirely to give a full equivalent of hydroxide, and there's no, for example, intact LiOH left when lithium hydroxide is dissolved in water. So pK is negative infinity. Weak acids and bases have pKa's and pKb's that are greater than 0, and so they don't fully dissociate, and we'll see what this means in more detail on a couple of slides. Let's briefly revisit now our definition of the acid ionization or acid dissociation or acidity constant and talk about what that means in the context of strong versus weak acids and bases. So Ka, remember, is the concentration of A-, the conjugate base, times the concentration of hydronium ion divided by the concentration of intact acid, Ha, at equilibrium. And we can define pKa as the negative base 10 logarithm of Ka, just a more human-friendly number. Given on the slide here are 3 different acids with their associated Ka values. Acetic acid is the first one, nitrous acid is the second, and HSO4- bisulfate is the third. And if we look at the K values, we go from 10 to the -5 to 10 to the -4 to 10 to the -2. And so the weakest acid with the smallest Ka that dissociates to the smallest extent is acetic acid here. And as we move down the list, Ka gets greater and the acid gets slightly stronger, although we would classify each of these as a weak acid with the pKa's all being greater than 1, and I encourage you to apply this formula, greater than 0 rather, and I encourage you to apply this formula, pKa equals negative log of Ka, to verify that. A quantity that gives us really a nice mental picture of how much an acid has dissociated in water is known as the percent ionization. And this is the ratio of the equilibrium concentration of H3O+ to the initial or total concentration of HA. So we take some HA, we dissolve it in water to some concentration HA tot or HA total molarity. It reacts with water to some degree to produce some amount of H3O+ at equilibrium. The ratio of that amount of H3O+ that has been produced at equilibrium to the initial amount of HA we started with, that's the percent ionization. And of course, we multiply by 100% to get that into a percentage range. So this gives us a sense of how much of that acid has reacted, right? When this is 100% for a strong acid, for example, that means all of the acid has been converted to hydronium ion. When this is 0%, We're dealing with something that is not an acid at all, that creates no H3O+ in water. In this problem, we're going to practice and apply our understanding of percent ionization, calculating percent ionization from a given pH value. So we know we're starting with a 0.125 molar solution of nitrous acid. It's a weak acid. That's actually all we need to know for the purposes of this problem. And we know that when we measure the pH of this solution at equilibrium, that pH is 2.09. And notice, the problem doesn't mention equilibrium pH, but you should assume whenever you're looking at a pH value that this is an equilibrium pH value. The solution has been allowed to come to equilibrium with respect to the acid ionization reaction, the reaction of the acid with water. So based on this given concentration of 0.125 moles per liter, this is the total concentration of acid in solution. And when you're given concentrations like this of an acid without any additional contextual information, assume it's a total or initial, from a fundamental equilibrium concepts point of view, concentration of the acid. From the given pH, we know the concentration of hydronium ion here. It's 10 to the negative 2.09. That turns out to be equal to 8.1 times 10 to the negative 3 moles per liter of hydronium ion. Now to find the percent ionization, we compare that hydronium ion concentration at equilibrium to the total concentration of HNO2, or initial concentration, before any reaction occurred. And when we set up that ratio and multiply by 100%, the result is 6.5%. Now, what does this mean conceptually? This is, roughly speaking, 1 in 20 or 5 in 100 of the molecules in the solution. And so it means roughly 1 in 20 molecules of HNO2 are ionized. 1 in 20 molecules have reacted with water to produce H3O+ and NO2-. The remaining 19 are intact HNO2. This is a weak acid, and this percentage makes this glaringly clear that only 1 in 20 molecules of HNO2 react with water at equilibrium to produce H3O+. To close, we should note that we can apply a very similar analysis to bases and the base ionization constant. So just to jog our memory here, the base ionization constant is the equilibrium concentration of Hb+, the conjugate acid, times OH- concentration, divided by the equilibrium concentration of the intact base B, or unionized base B. And as we did for Ka, we can define pKb as the negative base 10 logarithm of Kb. Here again, we have 3 examples of bases running from weakest at the top to strongest at the bottom, and let's verify that by looking at the Kb's. We've got 10 to the negative 11 in the case of the nitrite anion. We've got 10 to the negative 10 in the case of the acetate anion, and we've got 10 to the negative 5 in the case of ammonia, NH3. So Kb is increasing, pKb is becoming less positive, pKb is going down, and so we're going from weakest to strongest here from top to bottom. As we did with acids, we can define percent ionization for bases as the ratio of the equilibrium hydroxide concentration now divided by the total or initial concentration of base in the solution before we've considered its reaction with water. And here again, we multiply by 100% to find the percent ionization. So very similar analysis can be applied to bases as we just applied to acids.